In this episode, we're wrapping up the all-metal version of the RKDR 3 handheld gaming system, a hands-on demo, and then details on how to get one. Feeling lucky? Stick around. Today's a good day. We're finishing up the RKDR 3, all-metal edition. Aluminum body, brass buttons, blackout acrylic face, all the good stuff. If you've been following along, you know this project's been interleaved with lots of activities and other videos, but as promised, we're finishing this thing up today. In the last video, I showed you how we milled the body from billet aluminum, then polished it up to a mirror finish. Today we have a bunch of work to accomplish. We have to mill a couple of the final parts on the PocketNC, then we'll be sandblasting all the parts to give them a soft, clean look and feel. Next, I'll be milling the acrylic face and laser cut vinyl to finish it up. We'll also need to resin print the subframe for the circuit board. And with the new boards in hand, I'll be placing the components, testing, and getting ready for the build. Then finally, we'll be bringing it all together and demoing some games. Through the process today, I'll share some clues, sort of a treasure hunt of sorts, that'll give one lucky person the chance to win the final build. When you hear this sound, note the clue. It'll get you one step closer to winning the handheld. So stick around and good luck. To get started, let's finish off by milling the remaining power button. For that, we'll be using the PocketNC. In Fusion 360, I created a new setup project to pull in the PocketNC fixture model and the power button. I orient it over the center of axis, then hop into the manufacturing section to set up the tool operations. For this, I'll be using a 25mm rod stock to mill the part from 360 brass. In the setup, we identify the fixture, then select the machine origin. And with that, we first rough out the part using an adaptive rough and a 1/8 inch 3-flute flat end mill. For this operation, I'm running at 9,500 RPM, 15 inches per minute. On the passes tab, I'm running with an optimal load of 32 thou and a max step down of 78 thou. I'm leaving 20 thou stock to leave for the cleanup and finishing pass. And after the rough, with the same end mill, I run a 2D contour to clean up the sidewall of the button. Finally, I run a spiral operation on the face of the button to clean up the face and give it a nice finish. These are post-processed using the PocketNC processor, then sent to the machine. If you're not familiar with the PocketNC, it hosts its own web page on the machine. And this is how you manage and control the machine. Once it's on your network, you simply log into the website and we can upload and run the job. These three operations are using the same end mill, so before running the job, we'll measure the tool in the tool index that's referenced by the operations. Once that's complete, I run the roughing operations. With the rough complete, we head back into Fusion 360 to set up the finishing operations. First, using a 1/8 inch 2-flute ball end mill, I run a contour on the top edge of the button to round the off-axis face over. Then we engrave the face with the on-off label. Next, I create a couple operations to cut away the button from the stock to finish it off. With that complete, we post-process these operations and send them over to finish the button on the machine. Now in the last video I polished the body to a mirror finish, and over the last couple weeks I've had the chance to handle and play with the body enough to know that the polished surface is a pain to keep clean, and whether it's grease or fingerprints, it's a real hassle to maintain. I love the way it came out, but I decided to go a different route. So this time I've decided to sandblast all the parts and give them a soft, clean look. To do that, I picked up a small sandblast cabinet to surface these parts. The cabinet's designed for dental use and supports loading 2 different blast mediums to do something like coarse and fine-grained medium at the same time. The only thing to keep in mind for these things is to ensure that you have good air supply and a moisture trap. If you lose air pressure, then you'll have inconsistent etching behavior, and if you get moisture in the sand, then it'll have problems with the clumping. I'm also running a vacuum on the backside with a HEPA filter to keep any residual dust to a minimum. With that, using a circular motion, I blasted all the buttons, then the body, and while the pens worked pretty good for the small items, they were a little too focused for the large body. Eventually I removed the pen and used straight tube, which worked a lot better but did consume the media a lot faster. When I was finished, I washed the parts in warm soapy water and removed any residue. Then I baked them in an oven at 250 degrees for 30 minutes. This is to remove any additional moisture that was left over in the parts. The parts were then coated with an acrylic matte UV sealant. 2 thin coats and it was good to go. After coating, I applied the RKDR logo water slide decal to the body. This process is really easy. It uses warm water to release the decal from the backing paper, then slid off of the backing paper onto the desired location on the body. Once placed, I carefully remove any excess moisture and then heat cure the decal in place. When fully cured, I apply one final coat of the matte clear to seal the decal in place. With the metal parts finished, it's time to tackle the acrylic face. So back in Fusion 360, I prepare the operations to mill the part. The unique aspect of this acrylic face that requires it to be milled rather than laser cut is its countersunk pocket designed to accommodate the PS3 D-pads. For that, we'll use the 3D pocket operation to clear away material for the D-pad. Next, I use some 2D contour operations to cut out all the button and D-pad holes. Then finally, I run a 2D contour to cut out the face. With the face taken shape, I'll use a 1mm flat end mill to mill out the speaker slots using a 2D pocket operation. And finally, to complete the face, we need to mill a slot on the edge of the face. This slot's used for an O-ring that seats the face into the body. For this, I use a 1.5mm slotting end mill to create the O-ring channel. I post-process these out and run them on the Evo-One CNC. To hold the part down, I use a couple of strips of Nido tape, which is applied to the backside of the acrylic, then adhered to the wasteboard. Usually when using Nido tape, I'll use a weight to ensure the tape's fully adhered to the wasteboard before starting the milling operation. Now it's time to run the part. To mill these acrylic parts, the most important part is to be sure that you're using cast acrylic rather than extruded acrylic. Cast acrylic is a bit harder and has a higher melting temperature, preventing it from gumming up or melting during the milling process. The easiest way to determine what you have is that cast acrylic is protected by adhesive paper, while extruded acrylic is covered with generally a blue plastic material. When the part's complete, we can see the pocket and groove in the edge of the acrylic for the O-ring. To finish off the face, I'll laser cut a piece of adhesive black vinyl. This will be applied to the inside of the acrylic to black out the hidden areas of the interface, as well as to seal the speaker boxes into the subframe, but I'll explain that later. And for that, I'll use an app called Lightburn. After exporting the marquee and speaker covers from Fusion 360 as DXF files, I open Lightburn and import the files. Using Lightburn and a webcam, I can see what's on the table of my laser, and that allows me to arrange the cuts exactly on the material before sending the job. When I'm ready, I send the job and the cut's made. To apply the marquee to the acrylic, I remove the backing and place it face up. Using a couple buttons, I align the acrylic to the vinyl, drop it down, seating the vinyl to the acrylic. Most of the time this works out great, as long as the vinyl is not stretched while removing the backing. With that, we're good to go on the acrylic face. Next step is to print the subframe. To start, in Fusion 360, I export the subframe as an STL to 3D print. Now I'll be printing this in resin using the Formlabs Form 3 printer for its exceptional surface quality and repeatability. To do that, Formlabs has a proprietary slicer called Preform. I open Preform and import the model. Next, I orient the model to prevent having any supports on critical faces. Supports are what hold the part together as it's printing. To generate supports, I use 0.35 touch point and 60% settings to automatically generate the support for the parts in my orientation. While Preform does a reasonable job, sometimes it requires some manual work to add and remove desired supports. When I'm happy with the job, I send it over to my network connected printer and I'm good to go. This print took around 6 hours to complete. And when finished, I cleaned the part in 99% IPA, that's not the beer, it's isopropyl alcohol, to clean the remaining resin from the part. Next, let the part air dry for a couple of hours. When dry, it's time to remove the supports. This can be very time consuming, but using the 0.35mm touch points allows the supports to really peel off easily. Depending on your part orientation, like this one, the supports can encase your part, making it tedious to remove. This is where having good needle nose pliers can really help. With the subframe removed, I file and sand the part to remove any imperfections caused by the supports. Once it's perfect, I spray the part with a clear UV acrylic to finish it off. Now you can see the ported speaker enclosures. Lastly, I glue in some threaded brass inserts to prepare the frame for assembly. Okay, let's see. Buttons, body, acrylic, marquee, subframe, speakers, electronics. So I've got the new and improved boards and solder paste masks, so it's time to assemble one. To use the stencil, I have a simple screen print board that I mount the stencil to. I always 3D print a board alignment tool, which differs from project to project, but it's an easy way for me to align and print the boards with solder paste without having to register the screen with every board. With that done, I load a board, pull the paste, and head over to the electronics workbench to place the parts. Placing the parts by hand, I use an AmScope microscope. The optics have a wide field of view, but the video you see captured here is just a fraction of that. But it's useful in sharing the process with you. Important to note, with this circuit board, the majority of the parts are on the top side of the board. As it gets a little trickier to reflow parts on the second side of the board, I'll just be soldering the parts on the bottom side by hand a little later. Now, when I designed this board, I primarily used 0805 size components when possible to make it a little easier to solder by hand. At my workstation, I strap on my anti-static and clean the work area. Then it's just a matter of going through the BOM and placing each of the parts in the correct location. By the way, this video is sponsored by Altium. If you're interested in great electronics design software, take a moment to download the free copy and see what you're missing. I've put links in the description, and with Altium Designer, creating projects like these are a piece of cake. The efficient workspace has some of the best features in the industry, and through all phases of development, you'll be empowered to do your best work as you grow into its more advanced capabilities. The link below will allow you a free trial version of the software so you can check it out and see what enterprise class ECAD feels like. Now back to the project. When placing the parts, I generally go in this order. I'll first mount all passives. That's the resistors, capacitors, inductors, diodes. Next, I'll mount the remaining ICs, and after a final inspection, using a standard 4-phase reflow cycle, I bake the boards in my modified T962 reflow oven. This thing's pretty cheap on Amazon and works great for these short runs. When finished, I remove and let the board cool, and then do a visual inspection. If everything looks good, I flip the board and add the 200-pin SODIMM compute module header. This thing has a real fine pitch. I believe it's a 0.5mm, so you have to be careful not to bridge the pins, and for that reason, I flow the pads and use a generous amount of flux. And on a pin-by-pin basis, I flow each pin with a 1mm iron tip. Now, I've seen people run an iron across the pins to flow solder, and while I've had success doing that, I've had some traumatic experiences with that process as well. For me, flowing each pin when I cannot just run it in a reflow oven is the best option, as it provides the best results. I rarely have any issues when I do each pin discreetly. That said, once I've finished that process, I drag my probe across the pins to ensure that none move, which would indicate that it's not soldered, and then I'm good to go. Finally, I place a few remaining resistors and caps on the backside, which are all for the power supplies, and then a thermistor for the temperature controlled fan circuit. With that, the board's ready to test. Wiring up a power source, I first validate several test points are returning the correct voltages, indicating that the power circuits are performing as designed. Sometimes I'll need to reflow ICs as the pins are very small and sometimes they're not seated correctly during the reflow process. I try to be meticulous in the placement process to prevent this, but sometimes accidents happen. Learning to use a hot air rework station is essential for removing and reflowing parts. And now, with all tests passing, I solder the ILI 9341 header to the board. That's the LCD display connector. Now it's time to solder up the speaker connections. With the work complete, a compute module is loaded up and the SD card is installed and the board's fully tested. And once everything passes, the buttons and the power slider are inserted into the subframe and it's assembled with 4 M3 cap head screws. This holds it all together in a nice compact assembly. The battery is then fixed to the back side of the board and secured with some Kapton tape. This board is now ready for the parts and enclosure we prepared earlier. To assemble, first I take the body and insert the shoulder buttons. Holding them in place, I lower the subassembly into the body, guiding the volume wheel into the slot on the rear side of the body. When it's fully seated, I place the LCD screen in the recessed area. Final step is to add the O-ring on the acrylic face and ease it into place. As the O-ring compresses into the body shell, it slides down. I use a tool to ease or persuade the rubber into the channel. I've thought about using a lubricant of some sort to help slide it in, but I haven't found the right type that won't leave a residue. With enough patience and pressure, it mates perfectly with the body. Now would you look at that? Lots of patience and work comes together to a finished product. Wow. Of course, I've got to this point by being my worst critic. I'm never satisfied and I always find new ways that I can improve the design. But for now, let's take this thing for a run and demo some games.
Rewind.
Well, that was a lot of fun. Now this is a fun little project, but am I a gaming nut that goes to these extreme lengths to simply build and play a device of my dreams? Nah. But what it does do for me is hold my interest in such a multidisciplinary context to learn and apply designs, tools, and techniques. And while this is one more accomplishment in the evolution of the Arkader family, you can bet another version will be in the works again shortly. I'll continue to share, and together we'll continue to grow. If you like this particular episode, give it a big thumbs up. It lets me know you care. If you're new here, hit that subscribe button. It'll keep you in the know when new videos are released. Now, I'm going to be giving away an Arkader to one lucky follower, but to do this, it's not going to be easy. As you can see, a lot of work goes into this device, so you got to put some work in as well. To be entered in the giveaway, you'll need to subscribe to the channel, like the video, download Altium Designer software, share a link to this video in the social platform of your choice. Finally, using the clues you've collected during this video, send your answer to admin@diy.engineering for a chance to win the handheld. If you do all these things and you have the correct answer, you'll be entered for a chance to win the Arkader. Good luck, be safe, have fun, and I'll see you next time. Hey, if you liked the video, please subscribe to the channel. It's how we're building the community. Also allow me to bring better content. Also check me out on these other social networks. There's lots of cool stuff there too.